Okay, hi everyone. We're talking about the postulates of quantum mechanics, and in the previous couple of videos I talked about operators. Before we move on to the next postulate, I need to give you one important note about quantum mechanical operators. And that is that operators corresponding to classical observables are Hermitian. What does that mean? Well, to be Hermitian is a mathematical property that tells us how an operator relates to its complex conjugate. This is the central idea. You normally think about an operator operating on the wave function. If you took the complex of the operator and operated on the complex of the wave function, you get the same result. Right? Now, that's not mathematically rigorous, but it's the central idea. And you don't need to worry about the mathematical details here, but there are three important consequences that will show up throughout the course. I'll talk about each of these, but quickly, they are that eigenvalues of Hermitian operators are real, eigenfunctions of Hermitian operators are orthogonal, and the set of all eigenfunctions is complete. So let me detail for you what each of these means. First, eigenvalues of Hermitian operators are real. This should make sense, right? If you could measure it in the lab, right, which are what classical observables are, position of a particle, its energy, its momentum, whatever, it has to be mathematically real. To have a position of 3i makes no sense. Right? The eigenfunctions of Hermitian operators are orthogonal. What does that mean? Well, orthogonal means that the wave functions are, in some sense, perpendicular. Right? They don't overlap. And mathematically, we write that as follows. Right? The integral of two separate eigenfunctions integrated over all space is equal to 0. Right? That's what it means to be orthogonal. And there are a number of ways that this could be shown. So I'll have a worksheet for you where you'll do this through explicit evaluation. You can also make symmetry arguments or graphical analysis. And check out a worksheet for the first two. I want to quickly show you one problem where you can show this with graphical analysis. So here are two wave functions, psi1 and psi2. These wave functions are eigenfunctions of a Hermitian operator. The Hamiltonian operator corresponds to total energy. That's classical, therefore it's Hermitian. Use graphical analysis to show that these wave functions are orthogonal. Well, remember that orthogonal means that the integral of the product of these two is 0. Right here. So if I integrate psi1, psi2 over all space, I should get 0. And I can show this by making graphs. So the first thing you should do is sketch these functions and consider extrema and other possible zeros. So here we go. Here's my axes. I'm going to plot psi here. This is x. If I look at psi1, it's a sine function. Right? And my first note here is to consider extrema. So what I'm going to do is plug in x equals 0, which is my lower limit. The sine of 0 is 0, so it looks like this. The other extrema is L, right? Some constant, the maximum length available to the particle. If I plug in x equals L into this function, you get the sine of pi. The sine of pi is also 0. So I'm going to get a 0 there. And in between, this just looks like a sine function. Right? So this is psi1. If I plot psi2, it is also a sine function. Right? So at x equals 0, psi2 is 0. If I plug in x equals L, the sine of 2 pi is 0. And what you might recognize is that there's one other 0 in this function. If I plug in x equals L divided by 2. What you are going to get at the end of the day is a sine of pi. That is also 0. So right in the middle of the box, it goes to 0. In between all these spaces, I get a sine function. So it's going to look like this. That is psi 2. So I have now sketched my two functions. Consider the product function, identing zeros and the sign of the product. Here's what I mean by that. At the origin, both functions are 0. So 0 times 0 is 0. At x equals L divided by 2 in the middle of the box, right? 0 times some constant is also 0. At the edge of the box, again, 0 times 0 is 0. So I have those zeros. In between, in this region, psi 2 is positive, psi 1 is positive, therefore the product is going to be positive. And in this region, psi 1 is positive, but psi 2 is negative. Therefore, the product is going to be negative. So my red line here is psi 1, psi 2, the product of those two. Once you do that, you consider the integrated area. And I think you can convince yourself that, in fact, those are equal and opposite, therefore the total integral will be 0. Right? That's an example of graphical analysis. All right. See all of it. The third important consequence is that the set of all eigenfunctions is complete. What does that mean? Well, any arbitrary function could be written as a linear combination of eigenfunctions. Right? So I could take any function I want and I could write it as a linear combination of eigenfunctions. If you've taken you've seen some Fourier analysis, right? That's an example. So think Fourier analysis. Mathematically, we write f, our arbitrary function, is equal to c1 times psi 1 plus c2 times psi 2 plus blah, blah, blah. Right? F is whatever function, psi sub I are the set of all eigenfunctions, and c sub I are the weighting coefficients. What you need to know is a specific relationship, which is that the square modulus of c sub I, and I say square modulus because they can be complex. They can have imaginary terms in them. So the square modulus are the probability that the wave function is in the state described by eigenfunction I. So if I square those weighting coefficients, you get the probability that it's in that state. The last comment, and this is perhaps interesting to some of you, why do I put air quotes and say in? Right? Why can't it just be in this state? Well, at the end of the day, it has to do with how we interpret quantum mechanics. It turns out that outcomes do not exist outside of observation. So the fact that this is in psi 1 is not actually true unless you observe the system. And that process of observation changes reality. So this is a philosophical idea. And the person who understood this most clearly and explained it was Schrodinger. And he had a famous parable about a cat which was being poisoned inside of a box. So it's called Schrodinger's cat. And I will put some links to Schrodinger cat videos up on the web. If you like philosophical interpretations of quantum mechanics or just want a moment of diversion, you can watch both of these. I'll see if I can find one from Big Bang Theory. So I will stop here. We'll move on to the next postulate, and I will see you then.